Hello guys. In this video, we're going to explain the producer-consumer model, which is used in process communication, whereby one process writes to this buffer and another process reads from this buffer. And we're going to explain it as a motivation for the need of synchronization between two concurrent processes. So let's get started. Okay, so as I said, they communicate through a bounded buffer. So it's bounded, therefore it has a size. Let's see how to implement this in code. I've defined here a buffer size 10 and I've initiated an item buffer. Okay, so this buffer has items. What are those items? I've defined an item as a struct and it has a member called data. And I've initialized those variables in and out to 0, whereby in is the next free position for the writer to put something, okay, to write something into the buffer, and out is the next position to read from. Alright, this is how it starts then. In and out are pointing to the same location. Then what happens is that the first location gets filled, right? And when it gets filled, when I write, n is going to be incremented. But how did I write? Let's see the produce code. The producer code checks whether n plus 1 modulo buffer size is equal to out or not. To see whether the buffer is full. What that means is that n was here, it checks whether moving it here will make it equal to out. It doesn't. So we can write here. And then the n would be incremented from this location to this location. And then the same thing keeps happening. Okay, and here I have my in right now here, but notice that I still haven't read, okay? And that's why the out is still pointing there. And now I'm at this location. So in is pointing the next free location, which is 9. But in order to produce code, in order to allow the producer to produce data, the way I'm checking it is n plus 1 modulo buffer size is equal to out. And that would tell me whether the array is full or not. But n plus 1, okay, modulo buffer size. This modulo will allow me to loop over the array several times because I have to be able to fill these parts when they get emptied. And that's why I have to implement this buffer in a circular way, because whenever anything is read and the space is emptied, I have to replace it and fill it again, refill. So basically it allows me to keep looping over that buffer that I have, right? So this is what the modulus buffer size is for. Okay, but that's another note. Now I'm here. This is my next free location. And the way to check whether I can write something in it is if n plus 1, which is 9 plus 1, 0, modulus buffer size is equal to out, sorry. And 9 plus 1, which is 10, divided by modulus 10, the remainder would be 0, which is going to give me this index, and this index is equal to out. Okay, if this do nothing, it's assuming that my buffer is full, although I still have this location here empty, right? So I'm having a case where I'm getting the illusion that it's full when it's not actually full. And we've implemented it this way because when in and outs are the same, are pointing to the same thing, we're saying that it's empty. But if they're pointing towards But if the in plus 1 is pointing to the out, therefore it's full. And because I still haven't read here, I can have a case where I still haven't read here, and therefore I want to be allowed to fill in this location because this is not vacant. And this is a problem because it's a waste of space. You might say that it's not a waste of space for only one communication between two processes, but in fact the operating system has thousands and thousands of those processes that are communicating with each other, and this would be an immense waste of space. So in order to solve this issue, what we can do is create a global variable and call it count that verifies whether the buffer is full or not. Okay, so we're going to adjust our implementation of the code that we currently have. But before that, let's see how we can consume. So we looked at the producer code. Now let's look at the consumer code. So in order to consume an item, I would check if the buffer is empty, because if it is, there's nothing to consume. But if it's not, I will have a variable called item, which is of type item. Yeah, so I'll have a pointer to a variable of type item, and it has the memory address of the thing that I want to read from. So this is how it looks. I have a pointer here, and now I will be able to increment my out to the next position to read from, and so on and so forth. So I return that pointer, and this is basically the producer and consumer code. Now, in order to implement the revamped solution, I'm going to have an int count here, which is a global variable that I'll initialize to 0. And so instead of checking whether my buffer is full in order to produce in this way, I'm going to just check whether the count is equal to the buffer size. And here I'll of course have to implement, when the production is done, I'll have to increment the count by 1. As for the consumer, instead of checking it in this naive way, I'm just going to check whether my count is 0. And when it is the case that I've read correctly, what I'm going to do is simply decrement the count, because this is a free space that I can reuse again. And this is my new code, which is correct basically from the producer perspective and the consumer's perspective separately. But what happens if I run my program concurrently? Now, the problem is that if I'm running this program concurrently, and I've got like one thread executing count plus plus and another one executing count minus minus at the same time, what's going to happen is that count is 5 initially. But the problem is that this line of code here in C is translated to 3 lines of code in machine language or in assembly. And so is it here. And I really don't know whether the thread is going to allow me to successively execute these 3, or like there's going to be an interleaving between all these lines of code. In principle, when those 2 threads, my count was initially 5, this is going to increase it by 1, this is going to decrease it by 1. The logical solution to have is 5, right? In the end. So it's supposed to stay the same, but actually I can expect to have the correct answer, which is 5, and I can also expect it to have 4 or 6 when there's concurrency. Okay, suppose at T0 the producer thread executed the first statement, which is register 1 is equal to count, and therefore register 1 is going to have the value 5. And then at T1 it continued to execute the second line, and therefore the value it has now is 6. But it wasn't allowed to store this in count, so count still is 5. Before its work was cut off by the consumer thread, which executed register 2 is count, so now register 2 has 5. Alright, register 2 has 5, and the consumer again executed the second line of code, which is register 2 minus 1, and therefore register 2 had 4. Now then, the producer was allowed to execute counter is equal to register 1, and register 1 had the value 6. So the count was 6, but then this is the last statement that got executed, and therefore half count is equal to register 2. Register 2 had the value 4, so count is 4. And you can see that if there's a switching between these two, the value that it'll have is 6. However, if this was allowed to execute successively, and then this was allowed to execute, so, or basically atomically without interleaving those statements in machine code, I would have gotten the correct answer, which is 5. And therefore this creates a problem here, because I need to synchronize the work. I don't want, when this count here is being changed by a producer thread, for example, I don't want any other thread to change it at the same time. And this creates the need for synchronization. So this problem was explained in an attempt to motivate the importance of synchronization that I'll be explaining in the next videos. So I'll see you later on. But one last thing before I go, this is called a race condition. And a race condition is when multiple threads are competing to get the CPU time, and the last one, the result of the last thread will be actually the one to be updated. So here the last thread executed count equals 4, and the value that I had is 4. Alright, so if those two switched, the last thread to take the CPU would have been this, and the count would have been 6. So this is called a race condition. Yeah, this is it for this video, and I'll see you in the next one. Bye!